Hey everybody, our first video of the year, I guess. And we're going to talk about a subject that's near and dear to all of our hearts: derivatives. Derivatives are one of those things that are absolutely essential for understanding physics at the calculus level and really for understanding it well at all. We kind of phony our way around derivatives, but we really can't get away from it completely. So we're going to start with why derivatives matter. Let's say you have a position time graph here. And it has an easy curve on it. It has one of those, or an easy line. Well, that's pretty simple to understand. That's a pretty constant rate. You could pick any 2 points on it, and the speed at the beginning and at the middle and at the end are all going to be the same. But if I have, say, if I have a line that goes like this, now that's not so easy. And if worse comes to worse, I have a line that goes like this, then I'm in real trouble. Because if I want to find the speed at any point, it's not constant. You can see the slope is changing. On this one, the slope is almost kind of sinusoidal. So it's important that you're able to find at any time how much the slope is changing. And there's lots of ways to do that with tangent lines. You could actually draw a tangent line to the curve, like, say, this one. Sorry, I'm going to get you some. Okay, guess we're keeping that. I could take like this spot here, and I could get my ruler out and actually draw a tangent line and pick 2 points on it, figure out what the slope is, and I'm pretty good to go. The problem is that if you make whole functions, how can you find a function that describes each one? You basically have to draw a little tangent line at every point, and then it just gets tedious. So calculus is actually a way of zooming in on that point and actually drawing this tangent line here at a specific point. The actual definition, which I will get now, the definition is that for f of x equals whatever, okay, then the actual derivative, what's sometimes called f prime of x, the Leibniz would be df dx. This is what Newton really liked when he wrote calculus out. This is what Leibniz really liked. Newton was pretty good at making sure that Leibniz got almost no credit for it. But over time, people really came to love that form of it. It just described it better. It didn't have double primes, triple primes. It just was clearer. But the definition is if we took the function, the limit of the function f x plus h minus f of x over h as h goes to 0. And what that means is that this is if I look a little bit to the side of the function, plus or minus. And this is what the function says. And this is what happens if I make the difference, less and less and less. So I'm sort of zooming in on the whole line, trying to figure out exactly what the slope is. That's like the real definition of it. We're going to talk about taking derivatives of a bunch of different stuff, starting mostly with polynomials. Because if you actually go through and do this with like a h and whatever, you can actually prove these rules for polynomials. So So take the derivative of polynomial. If I have some function s equals x to the n. Okay. That means that, this is going to be fun to write. That means if I take the derivative of s with respect to x, that's going to be n, the power here, okay, plus or times x to 1 power less. So let's say that usually we're going to do these things in terms of time, at least initially. So we'll have like maybe I don't know, s equals 18t cubed. Well, s is going to be, we're just ds dt. Again, the derivative of the function s with respect to t is going to be 18 times the part with the t in it. That's going to be, n is 3, so it'll be 3. It'll be t is their variable we're taking respect to, and we're going to subtract 1 here, so it's going to be t squared. This is 54t squared. Okay, that's not terrible. And it turns out that as long as I mentioned, I said polynomials, I just did a monomial there. But if I have a string of polynomials, I just do the same thing. So if dv dx equals 9x to the 5th minus 3x cubed plus 7, then this is going to be 9 times 5, because that's n, x to the n minus 1, that'll be x to the 4th minus 3, which will be 3 times 3x squared plus 7. Notice there is no x here, so this actually doesn't get a derivative at all. There's no part of it with respect to x, so I don't have to worry about that. So if I simplify this, I get 45x to the 4th minus 9x squared. Okay. And that's dv dx. Again, all that matters is that you're consistent in the way that you do that. That's really all we're looking for here. In the next part, we will talk more about taking antiderivatives and about taking integrals too.